Hi, this is Dr. Bricker here with some hints for homework 8, problems 10 through 14, which are from chapter 28. And the first question we see here is, what is the de Broglie wavelength of a 159 gram baseball? So there's the mass. Make sure you put it in kilograms. Moving with the speed of 36 meters per second. That's the first part. And then the second part is, what is the speed? Part B down here. What speed would you have to have if the mass is the same thing, 0.159 kilograms, and the wavelength is 0.140 nanometers? Okay, so let's take a look at this. So make sure you read the rest of chapter 28, and there's some embedded videos. You can take a look at those too. So de Broglie came up with this relationship between momentum. So P is momentum. It's h divided by the wavelength. And then from what we did in Physics 220, the momentum is also equal to the mass times the velocity. So in the first part, we want to figure out what is the wavelength associated with a mass of 0.159 kilograms moving at 36 meters per second. Okay, we can use this matter-wave relationship here. And this is the same h that we had before, Planck's constant. Okay, so we have h over the wavelength is equal to m times v, and we're trying to figure out the wavelength. So doing a little bit of algebra, the wavelength turns out to be h over mv. Just be careful of the units here. H, joules times seconds, mass in kilograms, and then the velocity in meters per second, which is, that's what it's given, and that's good. So the wavelength will come out in meters. And then the second part is, given this mass and this wavelength, 0.140 nanometers, what is the speed? Same kind of idea, just use the de Broglie relationship to get the speed. So it looks like the speed turns out to be h wavelength times m. Now the wavelength is given in nanometers, so make sure that when you punch it in, you realize that that's times 10 to the minus 9th meters. So why do they give you such a small wavelength? Well, this is the wavelength that you'd have to encounter with this baseball. It would have to encounter an opening on this this size to have this wave characteristic come about. So how fast would it have to be moving? You'll find that this is a really big speed to have a wavelength this small. So it's, why do you not see this wave-like behavior of things like baseballs? It's because they're not moving fast enough. If they were, you would see the wave-like behavior, but you don't. So you'll find that interesting, I think, when you get this wavelength. All right, let's look at the next one. Okay, so here's the next one. Investigators have created structures consisting of linear chains of ionized atoms on a smooth surface. Electrons are restricted to travel along the chain. The energy levels of electrons match the results of the particle in the box model. Okay, so we're going to model these electrons as being a particle in a box. So again, make sure you review this section. This is, I think, 18.5 in chapter 18. And we can take a look at the associated energy levels. So for a 5 nanometer long chain, so that's the length of the box. The particle is stuck in this box, the particle being an electron. So that's 5 nanometers. Okay, and what are the energies in EV of the first 3 states? Good, so once we get the first state, it's relatively easy to get the corresponding states. Okay, let's take a look at this, and remember, it's an electron. Okay, so here we go. This is the formula for particles in a box. H squared, same thing, Planck's constant, 8 ml squared, and the mass, it's the mass of an electron. So 9.11 to the minus 31st kilograms. Length of the box squared in the formula. Luckily, we're given that. And then n is the energy level. So here we want to figure out n is equal to 1, 2, and 3. Those will be the energy levels. Now, if you look at this, we can get the corresponding energy levels by just multiplying the ground state by whatever energy level we want. So if you know the ground state, n is equal to 2 level is 4 times the ground state, because n squared, 2 squared is 4. The n is equal to 3 state is 9 times as big as the ground state. So once we get the ground state, Multiply it by 4, that gives you the n is equal to 2 state. Multiply it by 9, that gives you the n is equal to 3 state. So you're actually given everything here. So h, constant again, 8. This is mass of an electron. This is the length of the box. And then for the ground state, n is just equal to 1. So the ground state just turns out to be this number here, because you're multiplying it by 1. Okay, excellent. Let's look at the next one. Okay, again, you can review this part of the book here by clicking Review. What wavelengths appear in the system's emission spectrum? So here's the energy diagram. This is the ground state, which is 0 in this case. N is equal to 2 is 1.5. N is equal to 3 is 4. So this is not a particle in a box. This is just some random energy diagram, some quantum system here. Okay, so let's take a look at this. And we want the emission spectrum in nanometers. Okay, so first of all, how does this happen? Well, there's some transitions going on, and then when that happens, when you go from a higher level to a lower level, the electron emits a photon of the same energy. So the transitions here, you can go from 3 all the way down to 1. You can go from 2 down to 1, and then you can go from 3 to 2. So those are the different transitions. You can only jump in whole steps. You can't go to 2.5. There's no such thing. So from 3 to 1, from 2 to 1, or from 3 to 2. Those would be the 3 different corresponding quantum leaps, really. Here's what we can use to figure out the difference in energy between the states is hc over the wavelength. We saw something similar with energy of a photon in chapter 28 earlier. And that's also equal to hf. In this problem, they're asking for the wavelength, so we can look at the wavelength part of it here. We've got to come up with these different transitions. Okay, so we want the wavelength. That would be hc over the difference in energy. So we all know that hc is 1240 eV nanometers. I mean, you could punch in h, punch in c on your calculator, do it that way if you want to. I'm just doing it like this, and you'll see why. So let me do the 3 to 1 transition to begin with. You can do them in any order, but when you go from 3 to 1, the energy difference is 4 minus 0, so this would be 4 eV. Okay, so however you want to notate this, I'll just say that this is the 3 to 1 transition. So just figure out what this turns out to be. The EVs cancel out, and you're just left with nanometers. So it looks like 310 maybe? You'll have to check my math, but I'm getting 310 nanometers. That's the wavelength of the photon when you go from 3 down to 1. Then you've got to figure out the wavelength when you go from 2 to 1. Same thing, hc over the difference in energy, 1240 eV nanometers. And then when you go from 2 to 1, this would be 1.5 minus 0. So this would be 1.5 eV. And they do the same thing from 3 to 2. That difference in energy would be 2.5. Okay, and then list those 3 wavelengths, however I can't remember what they said, from least to greatest or greatest to least, whatever order, separated by a comma. All right, let's look at the next one. Actually, going back to that problem, it doesn't say what order, so whatever order that you want. And the next one. So in this problem, the 3 allowed energies are 0, okay, 0 eV, 6 eV, and 9 eV. And then what wavelengths appear in the emission spectrum. So it's a similar problem. So without going into too much detail, reconstruct your own quantum energy level. Just say this is 1, this is 2, this is 3, corresponding to 0, 6, and 9. Let me put this on a little bit of paper for you. You can take a look at it. Okay, so in the previous problem, they actually gave us a nice diagram. In this one, we can just kind of construct our own. N is 1, n is equal to 1, corresponds to 0. This is 6, and then that's 9. And then it really becomes the same problem. Okay, 1, 2, 3. Same kind of thing here. This is 9 eV, 6 eV, 0 eV. So in the emission spectrum, you really have the same exact problem. This is the only difference. You have to come up with this part yourself. But it's the same thing. The wavelength is hc over the difference in energy. And you should have 3 again, 3 different wavelengths. Okay, let's take a look at the final one. Okay, so this one is, let's see. What is the linear size of the smallest box in which you can confine an electron if you want to know for certain that the uncertainty in the electron speed is no more than 13 meters per second. So you don't know the electron speed, but you want to know it within an uncertainty of 13 meters per second. What is the associated uncertainty with the position? So you can't know the speed and the position exactly. You could know, you can confine it to a certain region of velocity, or speed in this case, and associated with that will be an uncertainty in the position, and that's what we're trying to figure out. So again, this is from chapter 28. You can hit the review section here and take a look at this concept. This is a Heisenberg uncertainty principle problem. So make sure you read through that section. Let's take a look at this. Okay, so the uncertainty in the speed is 13. It's an electron, so here's the mass. You'll see why we need that in a minute. And we want to know the associated uncertainty in the position. If you can confine the speed to within 13, how precisely can you know where it's actually located? And this is the Heisenberg uncertainty principle. Delta x times delta p, that product has to be greater than or equal to h over 4 pi. So this is from section 7 of chapter 28. Take a look at it. It's some pretty interesting stuff. So uncertainty in the momentum, let's rewrite that as mass times the uncertainty in the speed, greater than or equal to h over 4 pi. Okay, and what we're trying to figure out is the uncertainty in the position then. Okay, so this can be no greater than, or no less than I should say, h over 4 pi m times delta v. So I've just divided both sides by m times delta v. I put it over here, and this is the result. So we actually have everything here. This is where it's actually has to be confined. The smallest would be when it's equal to, and that's what they're actually asking. What's the smallest region where you can confine, where you might know where this thing is with this electron? So h, the constant that we had before, 4 pi, mass of an electron, and then the given uncertainty in the speed. So the smaller and smaller you make the uncertainty in the speed, the less and less you actually know where the thing is located. So that's how it works. If you try to really confine the speed to maybe you want to make it 5 meters per second, then you don't know where it's at. That gets bigger by the same corresponding fraction. Okay, like I said, the last 5 were bonus questions from chapter 28. Take a look through those sections and email me if you have any questions. Talk to you soon. Bye.